Hi everyone, I'm William Moses and I'm going to be presenting Enzyme, High Performance Automatic Differentiation of General CPU and CUDA Programs. This is joint work between myself and several other people. Differentiation is key to many algorithms in both machine learning and general scientific computing. In the machine learning realm, computing derivatives is necessary for algorithms such as backpropagation in neural networks, Bayesian inference, and uncertainty quantification. In the scientific computing realm, it's necessary from everything from modeling to simulation. When working with large code bases especially, or in particular dynamically generated programs, manually writing derivative functions quickly becomes intractable. As a consequence, the community has developed tools to be able to create such derivatives automatically. There tend to be three different approaches for computing derivatives. The first of which is to create a new differentiable DSL. Examples include TensorFlow, PyTorch, and others. In essence, the goal here is to provide a new language explicitly designed to be differentiated. This requires rewriting your entire program to be in that DSL, and of course, the DSL must support all operations that you want to perform that you had originally written in your previous program. This works quite well if the DSL matches the types of operations that you wanted to perform in your original program well. However, if this isn't the case, this isn't necessarily that fast or efficient to be able to rewrite. The second approach is known as operator overloading. Examples include tools like adept and JAX. In essence, the goal here is to provide differentiable versions of existing constructs. For example, adept replaces the type system of C++. Specifically, instead of having a double for your operation, you have an A double, which tracks all of the operations to later differentiate. In JAX, for example, you would, instead of using np or numpy.sum, you would instead use the jax.sum. Of course, these tools don't necessarily overload all of the types of functions that you may want to use, and thus you may need to rewrite some of your program to use slightly non-standard utilities that are, however, provided by these tools. Moreover, these tend to be dynamic in that they store the instructions and values to later be interpreted rather than to be statically deduced ahead of time, and this makes a rather large performance impact. The third approach is known as source rewriting. Such tools statically analyze your program to produce a new gradient function in that original source language. These tools must re-implement parsing and the semantics of whatever given language you want to differentiate. This also requires all of the code that you want to differentiate to be available ahead of time to be used by the tool. This consequently makes it somewhat difficult to use with external libraries. However, this tends to be quite fast in practice. All of these tools have the same general pipeline. First, you have your original program written in one of several languages, then an AD-specific tool for said language that emits new code in that language. And then you undergo the traditional compiler pipeline where you optimize your program and end up with a final executable. Let's see this happen in practice for a sample code. For example, here we have a function which computes the magnitude of a vector in O of n time. We have a second function which normalizes a vector in O of n squared time. Inside of that function, there's a for loop that sets the output of a given index to equal the input of that index divided by the magnitude computation, which consequently means that its runtime is O of n squared. An optimization that you might want to do is to pull that call to the magnitude function outside of the loop, reducing the runtime from O of n squared to simply O of n. If we were then to differentiate that program, first again we have the magnitude outside the loop. The corresponding gradient function would similarly have the gradient magnitude function outside of the loop in the reverse pass. This means that the reverse pass of the gradient would similarly be O of n time, like the forward pass. Now consider a scenario where we're to first do the automatic differentiation and then do the optimization. To begin with, our program would be O of n squared with the magnitude function inside the loop, and then the derivative reverse pass would have the gradient magnitude function similarly inside of the loop, for an O of n squared derivative. If we then attempted to optimize the function, we would soon see that we cannot pull the gradient magnitude outside the loop, as it uses a variable defined within the loop, dres, meaning that we would end up with a total runtime of O of n squared. As a consequence from this, we see that it's highly beneficial to be able to first optimize your program and then run automatic differentiation. Specifically, in doing so, you're able to get an asymptotically faster gradient, which is unfortunately not something that can be done via these existing tools. As a consequence, the enzyme approach aims to perform automatic differentiation after optimization by doing so at a low level. Specifically, first we have our original code, which is lowered to a standard compiler IR LLVM, which is then optimized. We then run automatic differentiation, then a subsequent pass of optimization, resulting in a optimized final executable. Overall, LLVM, you can think of it as a generic cross-platform assembly with well-defined semantics for the operations, which makes it nice to differentiate, as well as lots of other nice things. Specifically, there's a variety of different front ends that all translate down to LLVM, so we can write in one place differentiation simultaneously for Julia, C++, Rust, Swift, and the likes. Similarly, LLVM has a variety of backends. Everything from CPUs to GPUs, from CUDA, etc., can be differentiated all in one place. Moreover, LLVM internally has a large collection of various optimization passes and analyses, which are, as previously shown, useful for getting fast code, but moreover those analyses are incredibly helpful to being able to do a very efficient derivative. Let's look at this in practice. On the left, we have C code for ReLU3, a function which computes ReLU of x cubed. On the right, we have the LLVM for this function. This is shown in a CFG or control flow graph. Specifically, we have various nodes in the graph that correspond to a series of instructions, where edges between the graph denote changes in the control flow. For example, at the top, we have the entry block where we check whether or not x is greater than 0. If it is, we go ahead and compute x cubed. If not, we go ahead and directly return as shown on the bottom. If we wanted to differentiate that, the C code equivalent for that is on the bottom left, where we call this magic function enzyme autodiff that takes as its first argument ReLU3, the function to be differentiated, following by any arguments necessary. Going ahead and differentiating this function, the first thing that enzyme does is go ahead and try to compute all of the active instructions and values to the function. Specifically, an instruction or value is deemed active if it impacts potentially the derivative computation. This is quite useful for a variety of reasons. First of all, being able to do this analysis lets us ignore unnecessary instructions such as, say, CPU ID or other functions that don't actually impact the derivative computation. And as a consequence, we don't need to actually go ahead and differentiate these functions. In this case, the following values are active: the argument x, the call to pow, the phi node that says whether or not what's going to be returned, and the return value. For all of these active values, we go ahead and allocate and zero shadow memory that's used to store the gradient or temporary derivative of all of these values. Setting it to 0, we then continue the derivative computation. Specifically, then, for all of the active instructions in our original function, we go ahead and compute the adjoint for these. The adjoint is a special computation that takes the derivative of the output and flows it back to be the derivatives of the inputs. For example, on the left, we see the original part of the function computing pow of x cubed. On the bottom, we see what the corresponding adjoint computation is, which propagates 3 times x squared to the next part of the derivative computation. Doing some more optimization on that program, we see something that looks quite nice and is essentially the optimal handwritten gradient shown below as 3 times x squared if x is greater than 0. Doing AD on such a low level, though, has many additional challenges. For example, you lack at first a lot of the high-level information that you might otherwise have working at the source level. For example, look at the following function f, which simply copies 8 bytes from the source to the destination. If these 8 bytes happen to represent double data, then the corresponding gradient would be doing the left-hand side of one 8-byte floating point add. If, however, this represented float data rather than double data, the corresponding reverse pass would be to do two 4-byte floating point adds, which consequently these two differing size adds are incompatible with each other, and if you were to get it wrong, you would get an incorrect result. What Enzyme does to alleviate this is to present a new interprocedural data flow analysis that detects the underlying type of the data. Specifically, each value in the function has a set of memory offsets that correspond to the corresponding type at that memory offset. We then, for every instruction inside of the computation, define a specific rule that says how types flow through that instruction, and then perform a series of updates until we reach a fixed point. Let's take, for example, the type at the bottom left, which is a struct that first contains a double and then a pointer to an integer. And then let's say we take a pointer to that type. We can see on the right what the corresponding type tree would be for this value. First, we have a pointer, which is the type of x. Then inside of that pointer, we have our struct type that first contains a double at offset 0, then a pointer at offset 8. And of course, since that pointer was to an integer, that pointer itself points to an integer. From here, a couple of additional things that someone might want to do is to be able to specify custom forward passes or reverse passes. This is useful for a couple of reasons. First, if you have algebraic information that allows you to compute a slightly more efficient derivative or otherwise embed into the system some domain-specific information, you can specify that via attaching a custom metadata that specifies the corresponding forward and reverse pass. Moreover, this is also useful for integrating with other AD or generic systems. The second thing that's incredibly useful as a generic interoperability is the ability to differentiate across multiple files or across potential libraries. We do so by piggybacking off of LLVM's existing approaches for doing so generically. Specifically, we use link time optimization, which guarantees that prior to the link optimization phase, all of the source files have their IR available. This allows Enzyme to guarantee that all of the functions that it may need to differentiate are available prior to differentiation time. Similarly for libraries, we can use what are referred to as fat libraries that have simultaneously the LLVM bitcode for the function, as well as the object file. Again, ensuring that prior to taking the derivative, we have all of the IR we need to be able to potentially differentiate available. From here, we wanted to go and test how well this worked in practice. We took a collection of benchmarks from both Microsoft's machine learning focused AD bench suite and a couple of just generic technical interests. The main experiment we ran was that of Enzyme, in which we first ran the pre-processing optimizations, in this case just O2, followed by differentiation, followed by a post-processing optimization pipeline. To do a proper ablation analysis, we then compared this to first running the same Enzyme differentiation pass and then 2 rounds of optimization. This is meant to be an apples-to-apples comparison to what other tools might have to do while keeping everything else inside of the AD engine the same. This is because other tools cannot run optimization prior to differentiation. We also compare against the 2 fastest tools evaluated by the AD bench suite, Tapenade, a source rewriting tool, which is again followed by 2 rounds of optimization, and Adept, an operator overloading tool for C++, again followed by 2 rounds of optimization. From here, we evaluated that on our benchmark suite. Overall, let's first look at the comparison between Enzyme and the corresponding reference pipeline. So across the board here, Enzyme tends to do much faster, and it specifically does faster for everything except the FFT benchmark and the Brussels Rater benchmark. The reason for this is that the FFT benchmark and Brussels Rater benchmarks are already highly optimized, so any pre-processing optimization doesn't do that much. Looking across the board though, we see that there's an overall quite large speedup by being able to do this optimization first. Specifically, on average, Enzyme is 4.2 times faster than the corresponding reference pipeline. Let's now take a look at Enzyme versus Tapenade and Adept. In particular, looking at the LSTM and bundle analysis tool, the reference pipeline and Tapenade are roughly similar for these examples. So we can fairly conclude that a lot of the benefit that Enzyme gains over Tapenade for these comes from its ability to optimize beforehand. There are, of course, some differences between how Enzyme and Tapenade implement AD, and in particular, how they implement their internal caches, and that's why they're not exactly the same across the board. Overall, though, Enzyme tends to do quite well. Secondly, look at adept, the operator overloading tool. There's an additional overhead that this must also have. Namely, it has to store all of the instructions, potentially, that are taken to be able to later interpret and differentiate them. That's why you often see a higher overhead taken by adept. Specifically for ML researchers, we also produce two integrations into common ML workflows, namely the PyTorch-Enzyme and TensorFlow-Enzyme tools. These allow users of these DSLs to directly use Enzyme to import existing foreign code that's not written inside of either PyTorch or TensorFlow into their workflow and just directly use it without having to do a rewrite of the program. Now on to the fun part for this audience, automatic differentiation of CUDA kernels. So previously in this talk, we showed how Enzyme enables differentiation of arbitrary CPU programs without having to rewrite them inside of a DSL. Similarly, one may want to be able to import existing GPU programs or otherwise differentiate a program that calls some pre-written CUDA kernel. Unfortunately, it cannot currently be done without having to similarly rewrite the GPU program in a differential language such as PyTorch. Enzyme alleviates this by enabling reverse mode automatic differentiation of GPU programs. Specifically, in order to do this, we had to solve 4 different problems. The first of which is just generic to parallel ID of potential data races. The second of which is differentiating parallel control flow. In the GPU specific case here, that's SyncThreads. We had to make sure to be able to differentiate all of the relevant CUDA intrinsics, that's the thread and IDX and so on. And finally, we also had to make sure that we handled shared memory appropriately. Taking a step back from GPU-specific AD to a more general parallel AD, let's look at this problem. So on the left, we have a set function. What it does is it takes a value val and into 10 different locations in the array R, sets that array to equal that value val. Inside of it, since all of these array locations are distinct, we can have a parallel for doing the set rather than a traditional serial for. This is perfectly legal and perfectly fine. However, it does contain what's referred to as a read race. In essence, we're reading in 10 different threads the same value val at the same time. Of course, reading these 10 things at the same time doesn't result in any non-deterministic behavior, so it's perfectly fine again for the forward pass. However, when we go ahead and differentiate that leads to some interesting problems for the reverse pass, shown on the right. Specifically, the read race on the left becomes a write race on the right. That's because the propagation for the reverse of all of the differential values inside of dr have to simultaneously be pushed into the differential value of val, which all because they're in the parallel for loop for the reverse pass may happen at the same time. The fact that we may sum these things together simultaneously leads to non-deterministic or otherwise undefined behavior for what the final result of dval will be, and this is inherently not good. Generalizing slightly, there are 3 types of scenarios that we may see when trying to differentiate this type of memory. The first of which is we have some thread local memory. For example, on the bottom, that's a thread local variable inside of our device function. We can simply do the derivative for this as a non-atomic loader store. Since nothing else will touch it, it's perfectly safe. The second type of memory we may see is that all threads touch this exact same memory location. For example, in the middle here, we have a global variable y, and we do the same variable y in all threads. We can replace this with a parallel reduce over all of the values we want to sum into it. The third option is that we can't prove that it's either thread local or the exact same location. As a fallback, which is still legal either if it's thread local or the same location, is to simply do an atomic increment of whatever value we need to add into it. In this case, some generic argument to the function. Let's dive even a little bit deeper to this problem. So let's look at exactly what will happen for a load or a store of potentially racy variables. So first, the load on the left. We load from a potentially racy pointer into a thread local register res. The corresponding reverse pass from this is to load from the shadow of the register dres to get the current value of the derivative and similarly store into it 0. Then we do the corresponding atomic increment that we talked about earlier. In essence, because those first two things are thread local, since they are shadows of thread local registers, we can temporarily ignore this for the time being and just think that the gradient of the load of this is simply an atomic increment of the shadow pointer. Now let's look at the store. We're storing into a potentially unknown or race upon pointer some thread local register. Similarly, the reverse pass here is to load the current gradient out of the shadow pointer and then store it to equal to 0. Then we can do the traditional thread local load and store increment on top of the shadow of that register. Again, in essence here, the gradient of the store of the potentially raised upon pointer is first a load of the shadow, then a setting of it equal to 0. From here, we have enough of the framework necessary to talk about differentiation of more high-level functions, in this case, that of SyncThreads. So let's talk about exactly what SyncThreads is and why it might be necessary in this code. So a sync is only necessary if we want to be able to ensure that all of the code in the call to code A finishes prior to all of the code in code B executes. Diving in a little bit more generally, the sync is only necessary if A and B may write to the same memory or read from the same memory. Generically, there's 4 potential cases of this. Either case 1, we want to guarantee that all of the stores in A complete prior to a potential load of those values in B. Case 2, that all of the loads done in A complete prior to a potential overwriting store in B. Case 3, that all stores in A must complete prior to the potentially clobbering stores in B. Or finally, that all loads in A complete prior to all of the loads in B. Now, this last case is actually unnecessary to have the sync, since there's no additional guarantee from the fact that we've loaded A prior to loading B. Let's look at all of these 3 cases individually, and let's see if we can prove that the corresponding derivative of SyncThreads is to simply put another SyncThreads in the corresponding location in the reverse pass. So let's analyze case 1, in which we have a store, the sync, and then the load. So first, the store. The corresponding gradient of this store sync load is going to be the derivative of the load, in this case an atomic add, a sync, and then the gradient of the store, which is the load the current value, then set it equal to 0. And this is correct because the load of D pointer and the derivative of A must happen after all of the atomic adds and the derivative of B have already completed. So then that ensures that we have all of the things ready prior to our load there, which is great. Now let's talk about case 2. Here we have a load, a sync, and then a store. The corresponding derivative of this is first the derivative of the store, which is the load of the shadow and is setting it equal to 0, the sync, then the derivative of the load, in this case the atomic add. And again, this is correct. The reason that is correct is that all of the stores of D pointer will complete prior to any of the atomic adds in the derivative of code A, ensuring that any subsequent uses have all of the atomic adds done prior to their use in a later piece of the code. One might go even deeper here and ask, isn't there a potential race in the derivative of code B, pointed out by that arrow? And it turns out that we don't actually need to worry about this, since if there were a race on those corresponding loads and stores between the different threads in code B, that would be equivalent to having a write race in the original forward pass code B, in which we're storing to the same place in different threads. And so long as there exists no determinacy race in the original code, there won't be any problems with a determinacy race in the reverse code here. The third case is a store, a sync, and then a subsequent potentially clobbering store. So the corresponding reverse pass to this is first a load of the shadow and a store to 0, a sync, and again another load of the shadow and store to 0. And this is again correct. The reason why it's correct is that all of the stores to the differentiable pointer in derivative of B will complete prior to dA. And the correct behavior here is that we want only the subsequent load, or the last or clobbering load, to have its derivative incremented. And here, the corresponding pointer will only have its derivative incremented if it indeed was the clobbering store, which is exactly what we want. From here, we can then talk about all of the different CUDA intrinsics, since we've now shown enough infrastructure to be able to differentiate all of them. most of these CUDA intrinsics, such as the thread index and the likes, are actually inactive and inherently recomputable, and thus these are very easily directly incorporated into Enzyme without much additional special handling. As we showed earlier, the derivative of SyncThreads in particular is simply placing a new SyncThreads at the corresponding place in the reverse pass. Shared memory is a little bit special and requires handling by making a second shared memory allocation to act as the shadow or gradient accumulator for any potential active uses of the original shared memory. Now for the fun part. We can actually go ahead and differentiate a specific CUDA kernel. So on the top of this, we have the function inner, which says that y of thread index equals a of 0 times x of thread index. We declare the function enzyme autodiff, and then in the third global function dxpy, we call enzyme autodiff on the inner function, which we want to go ahead and differentiate. Translating roughly what the corresponding LLVM would be produced into a more readable C code, we get something that looks like the following in diffie-inner. First, we have the corresponding call to the forward code, y again equals a times x, exactly the same as before. Then we need to go ahead and compute all of these adjoints. So first we load the current shadow of y dy equals whatever was in there, and then storing it equal to 0. Then we need to do the increment of whatever we would have gotten out of dx. In this case, the increase we need to do dx via the chain rule is a of 0 times the dy or derivative of the output. Here we again do the atomic plus equals on dx equals that value. Now, if we were able to prove that every single thread would have its own memory location that isn't potentially written to or read from by another thread, we could go ahead and, as discussed earlier, remove the atomic increment and just have this be a thread local load and store. Now let's look at the derivative of dA. So here dA's derivative would be x times dy, which similarly has the atomic increment after the fact. Now, if we were able to go ahead and prove that all of the threads read from the same location, in this case a of 0, we could potentially replace the atomic increment with a parallel reduce, summing over all the values we would not need to increase the derivative by. From here, there's a couple of things that we need to talk about to be able to get the most performance out of differentiating these CUDA kernels. So if you have a generic function, Enzyme may need to cache certain values from that original function for later use in the derivative. For example, imagine you're differentiating a function x squared. The derivative of this is 2 times x, meaning that you need the exact value of x you computed from the forward pass in that specific location of the reverse pass to compute the equivalent derivative. Now suppose we actually write something like this into code. So we have some code on the right, f. And what it does is inside of a for loop, say some buffer temp equals some computation, then the output equals temp squared plus something else. And of course, we clobber over that buffer temp every iteration. It's being overwritten. And as a consequence, when we go ahead and compute the reverse pass, we have to go and cache that, since it'll have been clobbered over by our eventual use of it in the next iteration. Enzyme, by default, when it detects a value that needs caching, will go ahead and allocate memory. In the case of a CUDA kernel, via malloc inside of the kernel, which creates global memory. And this is potentially quite slow, since global memory isn't the fastest. Moreover, this may also overwhelm the amount of memory on the heap available on the GPU, potentially preventing it from running in the first place. As a consequence of this, we spent a fair bit of time adding additional optimizations that explicitly are aimed at reducing the memory usage, both on the CUDA kernel and just generically elsewhere. The first of this is to piggyback off of LLVM's existing alias analysis to determine the legality of potentially recomputing an instruction rather than having to cache it. In particular here, we also extended the alias analysis properties of SyncThreads to be more aggressive in our use case, so we can further avoid having to do these extraneous caches. The second generic property that you want to do is generally don't cache any values you don't need to. The easiest version of this is it's never used in the reverse pass, so there's no point to caching it. You can generalize this slightly to saying, oh, also, I may have already cached this value from a different instruction or in a different location, in which case, again, you shouldn't have to cache a second copy of it. Moreover, You may be able to specifically move certain amounts of caches outside of loops or generally reduce the total size necessary to be able to compute this cache, and whenever that's possible, just generically reduce the total memory needed for the cache. You should almost always do it, especially in this GPU case. A couple of other optimizations that we illustrate here include being able to do heap to stack, that's to say, take heap allocations, turn them to stack allocations, and if we can, bring them down to registers for the GPU especially. Very helpful. And then the last of these optimizations that we'll talk about here is especially important for GPU code, which is to say, don't cache memory, which is itself acting as a cache for other memory. Now, this happens to occur a lot in GPU code because of the use of shared memory. In particular, in various types of GPU programs, a common way of writing it is to say copy some large amount of memory into shared memory, then do some local computation of that, and say do that inside of a for loop. Of course, as the shared memory is being overwritten, then we would have to cache all of the uses of the shared memory. In this case, however, the shared memory is itself acting as a cache of some other memory. So rather than caching the cache, we should just go ahead and cache the original thing, and ideally try to reconstruct the shared memory for the reverse pass whenever we can. Combining these things together, we went ahead and did an evaluation of the GPU automatic differentiation on two proxy benchmarks available from the Department of Energy, XSBench and RSBench. We first evaluated the original forward pass version or original code for this. For XSBench, that happens to be about 1 second. For RSBench, that happens to be around 2 seconds. Next, we evaluated, similar to our reference pipeline, what would happen if we took the gradient with no additional optimization ahead of time. This is again similar to what an existing tool would have to do right now, because those tools cannot run optimization first. And of course, it just goes ahead and runs out of memory because of the amount of memory it has to go in cache. So we can't actually go ahead and run these. From there, we then took what the standard enzyme pipeline would have been, and then ran it on these two things. So we get something that actually runs, which is great, and seemingly the first time that we're able to do generic reverse mode GPU ID. For XSBench, it takes about 20 seconds for these standard optimizations, and RSBench, it takes more than 10 minutes, but does indeed complete, which is good. First time able to do anything is always good to have something come out of it, but still not necessarily the fastest. From here, we then went ahead and implemented a lot of these cache optimizations I talked about a second ago. And now with these cache optimizations, we're able to take the XSBench CUDA down to about 5 seconds, and we're able to take the RSBench CUDA down to about 8 seconds, which, again, not exactly 1 second for the reverse pass, but still definitely something. Oh, one other thing to note here. All of these times for the reverse pass are actually the time for both the forward pass and the reverse pass combined, so you can subtract out the forward pass if you want to just analyze the reverse pass alone. All of these were evaluated on a 2080 Super. So let's look at this entire story overall then. Enzyme itself is a tool for being able to perform reverse mode automatic differentiation of generic statically analyzable LLVM-IR. This provides two key benefits. The first of which is we're able to differentiate code in a variety of languages, since all of these languages eventually go down to the LLVM-IR level. These include, say, C, C++, Fortran, Julia, Rust, Swift, TensorFlow, what have you. It's fairly common for most front ends to go down to LLVM at some point. The second of which is by virtue of working at the low level of LLVM, we're able to first run optimization and then run automatic differentiation. And doing the previously discussed ablation analysis between running optimization first and then AD and vice versa, we're able to extract a 4.2x speedup from doing that alone. This and other high performance implementations inside of Enzyme itself allow it to achieve state-of-the-art performance when compared with existing tools. Moreover, unlike these existing tools, we're able to extend the scope of what's actually possible to be differentiated, and specifically differentiate GPU kernels. Enzyme itself is open source. Various links here at enzyme.mit.edu for documentation, as well as our GitHub if you want to go check out and download it. Would highly recommend going and taking a look at. And then finally, we also provide versions of Enzyme inside of both PyTorch and TensorFlow to allow ML researchers to import existing foreign code into their workflow without having to do a rewrite of their entire routine. There's a lot of people that we'd like to thank for various parts of the project, ranging from being master bug finders to helping looking over various parts of the draft of both this presentation and various papers. In addition, there's several funding agencies that we'd like to thank. I, in particular, was supported primarily by a Department of Energy grant, and several other collaborators at Argonne were also primarily supported by the Department of Energy. Valentin, as well as some others here, were also supported by grants from DARPA, as well as from the US Air Force. Overall, for all of the conclusions drawn here, they're that of the authors and not of the US government proper. Thank you so much. Any questions?